All right, welcome back. Apologies for the interruption. Let's continue where we left off here. So we are still in the middle of what I believe is section 10.6, and we are going to kind of start a new perspective on things. So remember, we're interested in these conserved quantities and understanding solutions in terms of the conserved quantities. So let's zoom into this idea, and we'll consider systems that are explicitly constructed from conserved quantities, that will have built in a conserved quantity. So, so this is kind of another perspective on what we were just talking about. We're going to look at a special case of differential equations that we'll describe now. All right, so suppose we don't have the system, and instead we start with what's called a Hamiltonian, which for our purposes, we don't even need a fancy name. It's just, some function of two variables, h. Then if we form this system, x prime is the y derivative of h, y prime is the negative x derivative of h, then h will be a conserved quantity. Again, so this right-hand side, you can think of as that matrix 0, 1, minus 1, 0, acting on the gradient of h. So that will have, built in to this construction, h is conserved along solutions. So just to remind you again, since this is the start of a new video, let me make sure we're all on the same page as to what I mean by conserved quantity. That means that if x and y solve the system, then the time derivative of h along the system, h is a function of two variables, but here we're, each of those two parameters is depending on a single parameter t. So it's a function of one variable at this point. And you can take the time derivative and it is 0. So again, what does this mean? That means level sets of h will be solution curves, and the gradient of h will be orthogonal to solution curves. We're saying the same thing, really. Critical points of h will be equilibrium points of the system, so on. All right, what about vice versa? How can you tell when your system arises like this? So by the way, we would call this system, this is a Hamiltonian system, a system which arises from, you start with the function of two variables and then form the nonlinear or general system like this. I call that Hamiltonian system. And how can you detect whether or not some, random old nonlinear system is Hamiltonian or not? Whether you can realize the system in this way. Well, all you really need to check is this one equation. If you take the x derivative of the thing here, and if that is equal to negative the y derivative of g, then the system is Hamiltonian. Just like, compare to asking the question, I shouldn't have used Q there. Compared to the question of how to determine if P of xy dx plus Q of xy dy equals 0 is exact or not. Remember, there was a similar condition. That thing that I just wrote down is exact which is to say the left-hand side is the total differential of a function of two variables, exactly when the y derivative of p is equal to the x derivative of q. That was the condition we needed to check to see if this thing was this a total differential of a single function of two variables. Likewise, we got a similar picture here. So, you could ask the question, okay, when am I in the situation where f is the y derivative of something and g is minus the x derivative of something? Well, we already basically saw the situation. The answer is when the x derivative of f is equal to minus the x derivative of f is equal to the y derivative of minus g, you could say, to match things up a little bit more closely. Okay. Well, what is useful about that? We didn't really explore this idea for when we were back over on this right-hand side here, where we were looking at exact equations. We, that was back when we were in the game of solving equations explicitly, which now we're not in. So, now let's actually use the function f, or in this case capital H, more seriously. So just notice, so if this thing is Hamiltonian, then we would like to extract our conserved quantity. So then to extract the function of x and y, the conserved quantity, the Hamiltonian H, well, then that's similar to the process of finding the function whose total differential is the left-hand side of the equation on the right. You have to integrate f and g to figure out what, because f will be the y derivative of h and g will be minus the x derivative of h. So h, you could say, is, okay, the antiderivative of f of xy with respect to y, and then there's going to be some constant, I'll call it phi, constant with respect to y, so it might still depend on x, and then you can figure out what that phi function is by taking the derivative of it and knowing it should be equal to minus g. So that's how you would find, we'll do this in practice, but that's how you would find what the h is. So this is a way, what is the point of all of this discussion so far on this page? The point is, you might happen to have a Hamiltonian system for, in which case there is a very concrete, good conserved quantity, h, which we would like to extract and study. How do you do that? Well, you can't always do that. Not every system is Hamiltonian, but there's a simple equation to check, which will tell you if it's Hamiltonian or not. If you check this thing and you're Hamiltonian, then you think, oh, okay, there is a quantity h, so that my system arises in this following sense. Take the y derivative of h, that's the top right-hand side, minus the x derivative of h, that's the right-hand side of the bottom equation. So then you could solve for h by integrating appropriately. And then that is the process of extracting the h, and then you can go from there depending on what the problem is asking, what you'd like to know. Okay. Now, so we'll look at an example of this in a second, but notice the following. Okay, so the linearization of these things, they're special. The linearization of Hamiltonian systems are special. So first of all, just by considering this is the right-hand side, the Jacobian of that function on the right-hand side is given as follows. You have a mixed derivative here, and then pure yy derivative in the upper right, minus xx derivatives, and then minus mixed derivatives in the lower right. Okay, so let's just think through what that means for equilibrium points. So here's a fact. So let's just get a look at what the determinant of j is, and talk through what's going on. Okay, so determinant of j, that is going to be minus partial x, partial y of h squared, since you know, the order in which you take partial derivatives does not matter, as long as h has good second derivatives. And then plus partial y, partial yh, partial xh. Okay, let's see what is going on. Okay, so if the the determinant of j is negative. By the way, let me say, okay, so just to back up a second. So critical point, or sorry, equilibrium point of the system, that corresponds to a critical point of h. It's the place where the gradient vanishes. Okay, and now you, if you recall, go back to vector calculus. There are criteria for what happens, how to classify critical points using the Hessian, which is this kind of this object that we have here. There's a second derivative test. So second derivative test for h will let us conclude the following fact. So if the determinant of j is negative, that only happens when it is a saddle point. Okay, you take the determinant of this thing and you get negative, that's a saddle point. Okay, and if the determinant of the Jacobian is positive, then it is actually a center. So that is a situation where you have a strict local max or min. So okay, so so when you have determinant positive, that is in other words, this critical point of h is a strict local maximum or minimum. You know, depends on the sign of one of the second derivatives. You know, that's not so important. But the point is, when the determinant of the Hessian of h is positive at a critical point, that means you have a strict local maximum or minimum. So, you know, h locally nearby this critical point, the graph of h looks like either this or incorrectly, like this or like a cap. Okay, in this case, you don't know what. So, okay, and let me also draw the picture for the determinant being negatives. That's a saddle point. Then you get a picture, usual saddle picture. You have opposite signs for the second derivatives. Right. So what can we conclude? So if you have a saddle point, then okay, not much you can conclude. Well, I mean, the equilibrium point is a saddle point. That's that's a generic behavior, so that'll be a genuine saddle point for the nonlinear equation. On the other hand, what happens if you have a actual strict maximum or minimum for h? You know, when you're in the situation where the determinant of j is positive. Well, then you have a genuine cup or cap-like shape. And what can you say is, well, there will be closed level sets. Right? You know, you have the say the minimum, and just take the plane that's tangent to like an xy plane. That's, you know, you imagine it's raised up to right where the minimum occurs, and then move it up a little bit, and you must encounter a closed curve which is by this construction, a level set of H. And so, since it's a level set of H, level sets of H correspond to solution curves, you have a closed solution curve. So down here in the XY, it might not be exactly a circle, it might be a little bit wobbly, but just from the fact that you have a local maximum or minimum genuine for H, that tells you you have closed solution curves. Okay, so that is, I say here it's actually a center, which is to say there are closed solution curves, and the linearization will have, have that shape. The real part of the eigenvalue will vanish. Pure complex. Very good. So that is the important fact for Hamiltonian systems, is their linearizations are special because they are actually second derivatives of, they're basically the Hessian of a, which is second derivative matrix of a function of two variables. And from that knowledge, you can use second derivative test to conclude things about the nature of the equilibrium point. Of course, second derivative test, you might remember, if the determinant of Jacobian is, if the determinant of the Hessian is 0, then the second derivative test doesn't say much. So then you can't really conclude anything. But that's non-generic, so let's not worry about that too much. Okay, let's take a look. Let's consider this. It's not a system right now, but it's a nonlinear mechanics type problem, because second derivatives or a nonlinear first order term. So you have that x squared going on there. All right, so let's first write it as a system, and then the claim is that it will be Hamiltonian. So let us try to do our. So let's try to find that first of all, and then let's use that to study the system. All right, let's take a look. So, as usual, we'll let V be x prime. So we get the system. X prime is, well, let's call it y. Let y be x prime. And so, equal x, x prime. Okay, so we get the system x prime is y, and y prime is minus 2x plus x squared. Okay, so now we want to figure out, is this Hamiltonian? So what should we do? Okay, so we're asking the question, is it Hamiltonian? Well, remember from that fact, well, okay, so let's, so in the notation from before, this thing is like f of xy, and this thing here is like g of xy. So remember, what is the condition we need to check? We need to check, so we need the partial derivative with respect to x of f equals minus the y derivative of g with a minus sign. Well, the x derivative of f is 0 since it only depends on y, and the y derivative of g is also 0. So 0 and 0 are the same thing. So for sure, the system is Hamiltonian. Okay, very good. By that, that means that, the remarkable fact that in order to figure out when you have two functions like this, if they're partial derivatives of a function of two variables, you just need to check that they satisfy partial derivatives commuting property that functions of two variables have. Okay, so now we want to actually find what H is. So just remember what this means for a system to be Hamiltonian. There is an H, a function of two variables, so that Well, the y derivative of h is f, and the x derivative of h is minus g. That's what it means to be Hamiltonian. So let's take one of these and start integrating and figuring out what h is. H itself, let's take the antiderivative of that equation with respect to y, is the integral of f dy. So that's the antiderivative just y, so that's 1/2 y squared. And then plus some function that depends on x, something that is constant in y. Okay, and then remember how this goes. To figure out what phi is, we have this partial formula for h. Let's take the x derivative of it. So partial x h, we know that has to be minus 2x plus x squared. So let's see, we take the partial derivative of this expression. So that's just phi prime. I know that has to be minus 2x plus x squared. And, oh wait, did I do that right? No. Be careful. I did not do that right. I made a mistake. There should be a minus sign. This should be minus g. So to figure out what phi is, we should integrate this. What do we get? We get phi is then equal to, and the integration constant is not really relevant here, but it's okay, so we get x squared and then minus 1/3 x cubed. All right, so the Hamiltonian for the system is the following. So we got 1/2 y squared. Then we get plus x squared minus 1/3 x cubed. Very good. So we have, first of all, determined that our system had a Hamiltonian, and then we figured out what it was. Okay. So let's try to take a look. What is going on with this Hamiltonian? What does this graph look like? Let's use it to analyze what are the equilibrium points of the system. So let's investigate the equilibrium points. Well, if you take a look at what needs to happen at an equilibrium point, well, y needs to be 0 and minus 2x plus x squared needs to be 0. Let's try and solve that system. Okay, so I mean, this is the end of the road for y, and then let's see what this means for x. This is x times, let's write this as x minus 2. So either x is 0 or 2. So we get two equilibrium points, which will be 2 critical points for h. With 2 equilibrium points. We get 0, 0, and 2, 0. Good. Now, let's use our newly acquired knowledge to determine what is the nature of these 2 points. In particular, we would like to see if there are closed solution curves or not. Because after all, this is an equation for motion. So we would like to know, do we have a system here where you could have a repeating motion, or is the motion going to get out of control? In the sense that, say, x could increase without bound. Let's take a look. So let's analyze the Jacobian. Here, where am I? Okay. So let's compute Jacobian. Okay, so let's see, let's take the x derivative of the first function here, that's 0. The y derivative of the first entry, that's 1. The the x derivative of that second entry is -2 plus 2x, and then the y derivative. The mixed partials are 0 here. All right, so let's see what's going on. So, well, let's compute what the determinant is. So, determinant of j is, well, it's 2x. Well, I guess it's has a minus sign. Well, it is important. It is 2 minus 2x. So at 0, 0, this determinant is 2, which is positive. Remember what that means? That means that h, the Hamiltonian, either has a local minimum or maximum there. So here we'll get, so this will be a center equilibrium point. And at 2, 0, the determinant is going to be, well, 2 minus 4, that's -2, and that is negative. So, and this is saddle point. Okay, so remember, so let's get a little picture of what is going on with this function. Well, this is totally not necessary a part of the analysis that the problem asks us to do. But let's just figure out if is this a max or min of this of h. So to figure out, so once you know you have a critical point or a determinant of Hessian is positive, then you just need to figure out is it a local max or min. You could see that by taking, say, either of the second pure derivatives, and the sign of that will tell you if it's a max or min. So just notice partial y of h is 1. That's that entry up here in the upper right. That's the pure y second derivative of h. 1 is positive, so the second derivative is positive in both directions at the origin. So that means we got a minimum for, so this critical point, so 0, 0 is a minimum for h. Okay, let's erase a little bit and yeah, I mean, I guess we can erase this Jacobian. And yeah, continue a little bit here. So we have the following. Well, let's also be a little bit more complete. Let's actually find the values of h at these two places. So just so we can be a little bit more complete. Notice, okay, so first of all, h at 0, 0 is 0, since there's h in the upper right there. You plug in 0 for x and y, you get 0. And h at 2, 0, what is that? That's when you plug in 2 for x, and you get 4 minus 1/3 times 8, and that is 12 minus 8/3, so that is 4/3. Okay, and we got a saddle point there. All right, so let's try and draw a little, well, okay, so let's try to draw two things. First of all, okay, so we have at 0, 0, we have a local minimum for h, and then over when we get to 4, 3, we have, this is going to be not the greatest picture in the world. Okay, when we get over to x is 2, okay, so sorry, that should be over here. We have the height of 4/3, and so we're increasing up here, And then this is a saddle point, so it should be decreasing in this direction and then increasing in this direction. So, you know, it looks like bowl shape here, bowl shape, and then it looks kind of like saddle-y. I don't know, your mileage is going to vary from this picture, but the point is you have a minimum at the 0, and then you have kind of curves. It's kind of like a negative downward shaping parabola along the x-axis, and then it is upward. You know, it's increasing like a bowl in the y direction. All right, which I mean you could have gotten from just looking at the formula, I suppose. But let's take a look more closely at the x and y plane. So here's x, here's y, and what did we find? Okay, so we got 1, 2. There's a special thing going on there. Okay, so just to be clear, we found this information that determinant of J is positive at the origin, so we have a local max or min. So that is so this equilibrium point is a center, and a true center in the sense that there will be closed solution curves. Closed solution curves. Okay, and then here that equilibrium point at 2, 0 is a saddle point. Okay, so what do we get? What is the picture? So, okay, nearby 0, there are closed solution curves. Many of them, in fact. Yeah, they correspond to these little level sets that are very close to the origin over there. But I drew on the graph as well. And then you got weird behavior at x. So okay, or at x is 2. So okay, you keep on going along, you'll get closed solution curves. These are all level sets. You know, I could draw them over here, but that picture's already quite a bit busy. And then important thing happens, critical thing happens at the level set corresponding to 4/3. And in fact, let me tell you now, note the level set xy, so that h of xy is equal to 4/3, the level set corresponding to 4/3, this is a separate, it separates between the two different behaviors. Generally speaking, I mean, it is a level set which is not a point, and it contains a critical point. That is what kind of makes it separatrix. Anyways, let me draw you the solution curve. It looks like this. Remember from implicit function theorem, from vector calculus, or if you have not encountered this fact before, but it is a fact that, you know, when you are looking at a level set which contains a critical point for your function of 2 variables, you're not guaranteed that that level set will look like a smooth curve. It won't look like you might have this like V-shaped thing going on here, you know, like we do. Okay, so this is the level set where H is 4/3. And it separates two different behavior. By the way, I kind of lied a little bit. So this is something like, I don't know, H is equal to 1/2 over here. You know, say one of these, let me do it in a different color to make my point a little bit more clear. So say this purple thing is H is equal to 1/2. That level set actually has a component that is over here as well. So on the picture, that's like over here and, you know, in there. So I just wanted to make a complete picture here. So it's you know, to reflect what's actually going on. But nevertheless, that's not so important for our analysis. The point is that well, it's not irrelevant. It does not, however, change the fact that there are closed solution. Okay, what else can we say? What else did I want to say? The following. Okay, so as you go above 4/3 and start looking at higher energy states, you could say, solution curves that correspond to higher values of the Hamiltonian, those look like these things here. So this is like, for instance, H is 2. And that would correspond to, over here on this picture, something like this. And then these, you get solution curves that are unbounded in y, unbounded velocity, you could say, and unbounded position. So now we have a kind of complete picture for this system, this nonlinear mechanical system, by analyzing kind of the energy function corresponding to it. We've had there's 2 equilibrium points for this system when you're just at the origin, so there's no action going on whatsoever. You start at rest with no velocity. Then there's also an equilibrium point over to the right when you're at position 2 and no velocity. That is a saddle point, an unstable equilibrium point. If you're at energy states in between 0 and 4/3, you have closed solution curves. So the motion is periodic. And if you're at levels, energy states above 4/3, then you have this other motion where both the position and velocity can become unbounded. Okay, and I've been talking about in physical terms, but we're just looking at an equation. It doesn't necessarily correspond to a physical situation. Okay, very good. So that is how to use, you're given some general kind of equation. Maybe it is a nonlinear equation for motion, or maybe you're just given this system of a nonlinear system. Here is one, kind of robust technique. Try and see if it's Hamiltonian, and if it is, then you have a very, very nice conserved quantity, and you can, in a straightforward way, classify critical points, and then describe whether or not you have closed solution curves. And talk about the different behaviors that solutions can have. We notice that generically there's only 2, these closed solution curves or these unbounded ones. That's a robust quantitative behavior of what is going on. Okay, so that's the technique. All right, now let us move on to the next section. This is split up a little bit. Okay, so let us look. This is section 10.7. Let's try to analyze, or develop a new trick in our bag of tricks. So this is very much related to what we were just talking about, but a little bit more general idea. Okay, so here's another method for studying stability or long time behavior. Generally, another technique for quantitative analysis of the nonlinear system. Okay, so here we'll just consider a general any dimension system of differential equations, could be nonlinear, and let's assume for now that it's one of these autonomous systems, which is to say there are no t's floating around. There are no t functions floating around in the right-hand side. Just depends on x. So for instance, like that last equation was also autonomous because it only depended on the velocity and the position. Okay, but anyway, so suppose you have a equilibrium point of the system. Here is something you can do. Okay, so let me back up and tell you a little bit, I guess, of a a background to this statement. So, okay, we have some point x naught, and we're going to be looking at a function v whose graph looks like this. So this is the graph of some auxiliary function v. But it will be, an example of, so it's kind of unrelated to the system, but it is related to the idea of having like something close to like a Hamiltonian or a conserved quantity along the system, but it's going to be worse than that. Anyway, so here's a prototype for one of these functions v that we're going to be using, one of these auxiliary functions, something like v of x, vector x is equal to, say, the norm of x minus x naught squared. Notice this function v has a minimum at x naught, and it's a strict minimum. It's literally a paraboloid centered at x naught at height 0. Okay, so that's going to be like the typical example of a function that we're going to be using. Although you don't need to have one that's exactly like this, but the point is that it has a minimum at x naught, and let me just say it has a strict global minimum at x naught. That's the point of that's the main feature of these functions that we're going to use. Okay, and if we'd like to use this as a, say, like how we use a conserved quantity or something which is monotone along solution curves, it will be useful to consider the following. So, so if x of t solves the system up here, notice the following. Then the derivative of v along the curve, solution curve, just observe the following. This is just equal to the gradient of v dot product x prime, and x prime is f. So this is f of x t. Okay, so that's just the background. This is describing some of the notation I'm going to be using, some context for what we're thinking about here. Okay, and just like when we were talking about monotone quantities or conserved quantities, it was relevant to know the sign of the t derivative of a function of two variables along a solution curve. So this is going to appear, this gradient dot capital F. By the way, this is just the chain rule in this context of you're plugging in a curve into a function of several variables and taking the derivative with respect to the parameter of the curve. Anyway, so let's see what the fact is. Okay, so suppose you find one of these functions which has a minimum at x naught. So let me just draw the picture again so that we're on the same page. Here is x naught. Here is v. I guess just the graph of v. So global minimum at v. So something like x minus x naught squared. Now here's the fact. Okay, if the gradient of f dot f, sorry, a gradient of v dot f has a maximum at x naught, which is to say that so i.e. partial t derivative of v is like minus near x naught, then x naught has to be stable. Okay, so that's like that is like the following picture. You have a solution curve x of t, and you are well, you don't need to be actually. Well, yeah, I mean, you need to be kind of spiraling towards that equilibrium point. So, in other words, the solution has to be going kind of downwards on the graph of the, the gradient of f dot f having a maximum means that the time derivative is negative, so your solution is kind of like sliding down the graph of v, you could imagine. So that will mean that x naught is a stable equilibrium point. Okay, if the gradient of v dot f has a strict maximum at x naught, which is to say that all nearby points, like x naught is the true maximum of gradient of v dot f among all nearby points. So you don't have like there's no other nearby point with the same value. Strict maximum. Then you conclude that you have a picture like I just drew there, where x naught is actually asymptotically stable. So not only do nearby solution curves not fly away to infinity, but they actually attract to x naught. Okay, so that is the idea. So this v is kind of acting like a one of those conserved quantities, but it's not like conserved. You want to arrange for v to be like actually not conserved, but actually decreasing along the differential equation. Then you can conclude things like, oh, x naught is stable. So this is this method of trying to show that equilibrium of analyzing equilibrium points is kind of more flimsy in the sense that v doesn't necessarily have very much to do with the differential equation. V will almost always be something like this, like just the distance to the whatever critical point you're looking at. So it's a little bit flimsy in that sense, but it's more flexible because you don't need to necessarily exactly find a Hamiltonian or something like that. So you don't need to do a calculation necessarily. But let's see, and it also works in all dimensions. Let's see what happens. Let's try to do an example. Oh yeah, and again, this is just some notation. The gradient of v dot f is sometimes denoted like this. It's also like dt v of x of t. They all mean the same thing. Okay, so let us do an example. Okay, so here is another like nonlinear motion equation, and let's use this method of oh, I never said the name. How do we say the name? Lyapunov, method of Lyapunov. It's just basically this the method is just that observation, this fact. If you can find a function v which has a strict minimum at x naught, looks like a paraboloid centered at x naught, and you can show that near this equilibrium point x naught, the gradient of f or gradient of v dot f is maximum, then you can say you got a stable point. Okay, let's take a look. And then sometimes you can go a little bit further. Like we'll see this in this example, but sometimes you can only say, it looks like you can only say that x naught is stable, but then when you think about what form the right-hand side of the equation actually has, then you can say, oh, actually, there's only one way in which it fails to be a strict maximum for gradient v dot f. And just by looking at the form of capital F, you can say that that's not going to be an issue. We'll see what I'm talking about in this problem. Okay, let's take a look. Okay, so let's do our usual thing and convert this into a system. Oh, 1 second. All right. Yeah, so let's let v be x prime. Well, let's go back to y. I like the y. Okay, so let y be x prime. Then this becomes the system. X prime is equal to y, and y prime is equal to minus x prime, which is y, and then minus x cubed. Good. So, well, in particular, this is not Hamiltonian, so we can't use the method of the section 10.6, because the x derivative of the top thing vanishes, but the y derivative of the bottom thing doesn't vanish, so not Hamiltonian. So if we want to analyze, notice 0 is the equilibrium point for this system, obviously. So if the right-hand side vanishes when x and y are 0. If we want to analyze that equilibrium point, we cannot rely on a Hamiltonian to, compute and then study and do the work for us. Instead, we have to do something like this kind of flimsy method. Flimsy, not the right word, but the more general, more flexible method of Lyapunov to analyze the stability of the origin. Okay, well, let's see what we can see. Let's see. Okay. Okay, so it's not an exact science, but usually the thing that you want to consider, the function that has a strict minimum at x naught or at the origin, is just going to be the parabola. So let's let v of x and y be, just to be clear, we got a little picture going on here. Is the xy axis. We are looking at the origin. We want to do that above method to hopefully show that the origin is asymptotically stable. So what do we see? Oh yeah, so let's let v be the typical thing. So that's x squared plus y squared, typical parabola. Sometimes you might want to consider like something like x to the 4th plus y squared. It just depends on the equation. I think this will be. I think this will do the trick for us. Okay. Good. So now let's compute. Let's compute v gradient of v dot f. So, okay, gradient of v is, okay, gotta take the x derivative here. You're gonna have 2x there, and then y derivative down the bottom here, that's 2y. Okay, easy enough. And then dot product with f, which is y, and then down here we got minus y minus x cubed. We need to study this thing because if it is maximum at the origin, we're in good shape. Okay, let's take a look. Okay, yeah, so this dot product is 2xy, and then we got minus 2y squared, and then minus 2yx cubed. Okay, so that is the, this is the v dot from that I mentioned earlier. Okay, so we compute this dot product, and this will be an educational experience here. this is a little bit of a mess. Hard to see what's going on here. So hard to see if the origin is max for this function. In particular, you know, that minus 2y squared, that is, you know, good from the perspective of wanting the origin to be a maximum. And then you got that other business messing our lives up a little bit, these other two terms. So there's no good. I mean, you know, may or may not be good, but let's try a more straightforward. So let's try again. Let's try let's modify our choice for v. Notice what, I mean, you can hope, okay, notice what's going on. We got these two bad things. Notice this first one, the minus 2xy, well, that came from the x component, the x derivative of our kind of our v function. And if, you know, we could arrange for that to have more powers, you know, have a higher power of x. Let me show you what I mean. If it had a higher power of x, then maybe it could cancel with this minus 2y x cubed. So let's try the following. Let's try v of xy is equal to 1/2 x to the 4th plus y squared. I think that'll be a good choice. Let's see what happens. Then gradient v dot f is, okay, gradient of v will now be 2x cubed in the first component, and then the second one will be the same 2y. I got that product with y and then minus y minus x cubed. Okay, so now look what happens. You got the 2x cubed y minus 2y squared. That's the thing that we liked, and then we got a minus 2yx cubed. And look at that. We chose just the right thing in our v function so that this just went away. And now, you know, this dot product, this v dot, is just minus 2y squared. So the origin is a not strict maximum, because this v dot looks like you know, a parabola that's been translated along the x-axis, opening up in the y direction, or not opening up, but it's a parabola in y. Okay, good. So what do we conclude from this? So all we know is that the origin is stable. So well, let's just call it 0 is stable, equilibrium point. But that's not what the problem asked for. I wanted to know it's asymptotically stable, that it actually attracts nearby solutions. This can't, you know, the job's not done yet. Okay. So we'll need to take a closer look at the actual right-hand side of the equation. So note, the problem, which is to say the reason why this function v can only tell us that the origin is stable and not asymptotically so. The only problem is the x-axis is the x-axis. Namely, if we have, say, a solution that starts on the x-axis, so in other words, if a solution x of t has initial conditions with 0 y component, you know, I don't know, x naught follows 0, then we don't know, we can't say that the limit as t goes to infinity, t goes to infinity, of x of t is the origin. Okay, that's the problem. Initial conditions that lie on the x-axis. This is the problem. However, let's just inspect the f, the capital F, x. That is the vector. Let's take a look again. That is y. This is bold x. So y, and then minus y minus x cubed. Okay, so well, if the y component is 0, this will just be the vector 0 comma minus x cubed. So what we find is that this, the slope field, just get a little rough picture of what the slope field is doing along this axis. It is actually pushing you off of the y-axis. So over here, it pushes you upwards, because these are all the vector 0 comma minus x cubed. This is just what the phase portion looks like along the x-axis. So we were worried, okay, maybe if you have initial conditions that are on the x-axis, you might not attract to the origin. But we notice what actually happens is if you start on the x-axis, you immediately get pushed off of it. Okay, and then what we said before should tell us that that solution will then go back to the, get attracted to the origin. And so, note, if initial condition x naught is like some, like x at times 0 is x naught 0, then for any positive time, this does not lie on the x-axis for at least small values of t. So you immediately get pushed off of the x-axis. And so this is a little bit hand-wavy at this point, but let me just say, this will be a general, the logic that we're outlining here is in fact general. So here's the following. There is a fact which says the following. So if we're in this situation, so if gradient v dot f has a non-strict maximum at some critical or equilibrium point x naught, then you can say that the limit set of nearby solutions must be contained in the wherever the gradient of v dot f vanishes. So if it's not, then limit set of nearby solutions is contained in the set of points where gradient of v dot f is 0. So what does that say for us? Well, it kind of tells us that our logic is correct. It says that, okay, so the gradient, so the area, the region where the gradient of v dot f for our situation vanishes is the x-axis. Now we know that from this fact that the limit set of nearby solutions has to be contained. At this point, we know that 0, the origin is a limit set, but maybe there could be more to the limit set of nearby solutions. Maybe, for instance, the whole positive x-axis could be a limit set, in which case we could not conclude that the origin was asymptotically stable, only merely stable. But what this says is that, okay, so the limit set has to be contained in here, but just the x-axis can't be a limit set because the capital F points out of it. Points out of it. Away from the origin. So long as we are, except at the origin 0, 0. Okay, so what that allows us to do is, as we were saying in this purple note, is okay. We were worried about what if you started out on the positive x-axis or nearby it? Would you just be attracted to the positive x-axis away from the origin? Well, it doesn't seem like that because the capital F actually forces you off of the positive x-axis, and this fact allows us to make that argument rigorous. Namely, it says that limit set of nearby solutions actually must be, in fact, contained in places where the gradient vanishes. But we can say the only place on the x-axis where which can be a part of a limit set is actually the origin, because the right-hand side of the equation pushes you out of the positive x-axis if you're not at the origin, like we just saw in the picture, pushes you orthogonally out of it. Okay, the upshot is, so the only point in the set where gradient of v dot f vanishes, which can be a limit point, is the origin. So the origin is not only stable, but it's asymptotically stable. Okay, very good. Yeah, it's getting pushed definitely towards the origin. Might spiral a little bit, but it's getting pushed into the origin. Very good. Maybe you could imagine, oh, what if you chose like a really much better form of V? Then maybe you would be able to have seen this right off the bat. Maybe you could have chosen a V which makes the origin manifestly stable, like a strict maximum for gradient V dot F. But that's not always possible, and that's not really the point of the method. The point is you don't have to think too hard about what V is. You just need to make sure that you choose V so that gradient V dot F has a maximum at the equilibrium point. And then if you're in this borderline case where, oh, I'm not sure, it's not a strict maximum, because here we had a maximum all along the x-axis, then you can say, okay, I know we got to have, the limiting set has got to be along this x-axis. And then you have to analyze the actual form of the nonlinear equation to argue whether or not, the origin in this case is actually attracting nearby solutions. We know it attracted it from above and below, but not necessarily from the side. But if you look at the form of the vector field, then you can see that it's not possible. It can't approach from the side. It gets pushed off if you're on the x-axis. All right, so that was a little bit wordy, convoluted. We should do some more examples of this in the future on Friday, perhaps. But for now, that's done. This is already quite a long lecture. Thanks for your attention, and I'll see you in class.